All right, hit record. So now it's going to look like so now it's going to look like that. And I'm just going to kind of give you some highlights. This is going to save me from having to write a lot of things down. And, you know, it is being recorded, but I encourage you to take notes. It'll be recorded. It'll get posted. I do want to mention something about that. So, you guys will have your own playlist. Because I haven't posted anything for you guys yet. It'll say, Math 3A, that's the Tuesday, Thursday class, grade 2022. And there's been one video, a welcome video from yesterday. Yours, you'll see something here today, Math 3A, Monday, Wednesday, spring 2022. And so I have a playlist for every class that I teach. That's where you'll go and you find the current video. There will be a link that you can always click on the home page from Canvas. But also, here's what I do. As soon as I'm done uploading, as soon as Zoom sends me the video, then I upload it to YouTube. And as soon as YouTube is finished uploading it and doing all of this stuff, I send you the link from Canvas email and send it out to the entire class all for it. So you will get it directly in your email, and you can just click on it, and you don't have to go to the YouTube playlist, click on the video yourself. Now, here's what I want to make sure we're clear. The email I gave you on the syllabus either one of these. This is either one of these is what I want you to use to contact me from your own personal account, not Canvas. But here's all I'm going to use Canvas for is to post anything that I give you or hand out in class. In case you lose it, you can always download it, click on it, or whatever. But I email the entire class. That's the best access I have. I can just click on the entire class and send it. When students just hit reply, when I send out the YouTube video link, hit reply, that's the quickest way for you to contact me. But it's coming from your Canvas account. If you accidentally hit reply all, it's going to everything. Number two, if I accidentally hit reply all to you, then I'm going to, and if you ask me for your grade, then I send up your grade to everybody, which I don't want to do. Which is why if you want to communicate with me on email, use your school account, not Canvas, but your school account or your private account. Just make sure you tell me who you are, first, last name, Monday, Wednesday, not 3A, so I know you're not another class. And I will communicate you through my Outlook email and not Canvas. That's the best way. The only thing I'm going to do is use Canvas for it when I use it. Really, and the other thing about it, you reply alls. I can't separate your email out from that whole list of emails. I like to archive when I have correspondence with that. I like to archive it and put it into a folder so I know what's been going on in the conversation. So we make sure I make sure that if I don't, then I'm scrolling through 5,000 messages. Maybe I just have to figure it out. So, library of parent functions. Library of parent functions. So here's our list of parent functions. So every function that we're going to be studying is based upon this list of kind of functions. And then all you got to do is about shifting up, shifting down, shifting left, shifting right. Stretch it, you can squish it, you can tighten it, you can narrow it, you can reflect it left and right, you can reflect it up and down, you can reflect it twice, left and right, up and down. So transformation on our basic set of parent functions. Okay. This is our list of parent functions. Everything we're going to do in chapter 1 is based on these five specific parent functions. And we're going to go linear in 1.2. Okay. We're going to really get quadratics in 3.1, cubics in 3.2, and rationals in 3.6. Okay. But we're going to do a little bit, we're going to do a lot of calculator stuff. You're not going to have to graph by hand, but you can do a lot of calculator graphing. So I'll be using the PI-84 as a demonstration. So if you haven't checked out a graphic calculator yet, make sure you have access to one that will really help. The library, right through the glass doors, and it's right in front and behind the glass doors, a little bit to the right. It's just right across that entryway on the right-hand side. The chip they implanted doesn't track it. So the first one can't be any more clear than what it looks like. It's a linear function. So that means f of x equals x is going to be a straight line. But what makes it different than all the other functions? It's x to the first power. It's x to the first. In Algebra 1, you first learn about this as y equals x. Y in the rows is mx plus b. Yeah, absolutely. I know I'm a wide body. When you sit there, because I'm right-handed. But that's how you get transformation. The plus b slides it up and down. M changes the angle of that line. So But it's all based on that simple parent function, y equals x. The slope is 1 over 1, so this would be 1, comma 1. This would be 2, comma 2. When x is 2, y is 2. When x is 3, y is 3. When x is negative 1, y is negative 1, and so on. So that's y equals x. If you do y equals x plus 4, then this gets shifted 1, 2, 3, 4 units up. You take the parent function and you add 4 to all the y answers. So everything is now, this was 0, it's now at 0, 4. The y is 4. When you plug in 1, the answer is 1. But you're going to add 4 to that answer, so it's now going to be at 1, 5. It's been shifted up. When you plug in 2, you got 2. But now you take 4, add it to that answer, when you plug in 2, you're going to get 6. It's the exact same graph, but just manipulated, shifted, transformed, translated. So we start with the parent. When we graph something, no matter what class we're graphing in, when we first learn about graphing linear equations, we make tables. And we get some numbers, we plug them in, we got ordered pairs. And we wanted to see what it was going to look like when we did that. Then we start to see, oh, you know what, there's a pattern going on. And then we start to see, I don't need to plug in numbers anymore. I know exactly that this is always going to make 5 if I have a y to the first and an x to the third. And I know what the 2 is going to do to it, and the 3 is going to be the slope. You start to put pieces of it, and you no longer plug in numbers. That's the key. But you start by simple substitution. Quadratics. In algebra 2, you start with quadratics. A quadratic is because it's x squared. X to the first is in here. X squared is a quadratic. Okay? Which means the shape of the graph is a parabola. So the shape of the graph is a parabola. Looks like that. Because no matter what you plug in and square it, it's always going to come out and be a positive number. If you plug in 3, you get positive 9. But if you plug in negative 3, negative squared, positive 9. So you can't get numbers down here. You would get numbers both sides, left and right, positive y values. So that's the shape. It's a curve. Now, the most interesting thing about the quadratics, everything that flies through the air can be written in the equation that explains its types. And in time, it's always a parabola. Anything that goes through the air is always in the shape of a parabola. Even if I throw it straight up and it comes straight down, that's just a parabola that's really narrow. And you can find a square function, a second degree equation, that explains its type, and you can find because of controlling it. And when you get into calculus, we'll probably hit it a little bit this time, but when you get into calculus, the position, the height of the object at any given time is equal to 1/2 times the acceleration due to gravity times how long it's been released, the amount of time it's in the air, squared, plus the initial velocity with which you can. This is not going to go up unless I put some initial velocity to let it go. The initial velocity times time, and its height is position with respect to the surface of the one more number into this position. Am I releasing it? Am I standing in a hold, and then when I release it from the position over there, straight up, position 0? Or since I'm about 5'8", when I release it right here, I'm releasing about 4 feet 8 millimeters. That would be 4 feet 5 inches. Let's make 4 feet 6, 4.5. So acceleration due to gravity figured out by Newton. Maybe it was Galileo. Anyway, Galileo figured out this kind of equation in 1500. Acceleration is negative 32 feet per second squared. So negative 32 feet per second per second. Now, negative because it's making something go accelerate towards the center of the earth. Direction. In meters, it's negative 9.8 meters. That's a constant on the earth. If you're on the moon, what do they always say about how much you weigh on the earth? So it's on the earth. Well, lighter, but by what ratio? What? Close, there's refraction. About 1/6. So the acceleration due to gravity on the moon is 1/6 of what it is on Earth. If you weigh 180 pounds, let's say 240. 240, 1/6 of 240, I would feel like I weighed 40 pounds. I would feel like a weight. I would feel like my mass. What about mass? Those other measurements. So why don't you see the astronauts, late 60s, 47, why aren't they jumping 8 feet off the ground? You gotta remember they have hundreds of pounds of life support on their backs. Because where the ground moves, it's 200, no. It's 200 something degrees in the sunlight and negative 200 something degrees in the shade. Because there's no atmosphere. The atmosphere is what holds in our temperature. So a nice, comfortable 130 degrees. But on the moon, you stand in the sun, you're at over 200. Stand in the shade, you're negative 200. So you have to have that space suit on to protect you. It's your air, it's your food, it's your water, it's your bathroom. That's why they're not leaving them into the air. One thing that also Galileo proved in 1500. This is why Galileo got in so much trouble. Galileo was a devout card-carrying Catholic. And at that time, in the 1500s, who was in charge, basically, who had more power than kings and queens? Who was in charge of educating the people? The church was teaching Aristotle concepts. And not in terms of religion, not in terms of faith, but they're in charge of teaching science. In charge of teaching everything. Aristotle believed in a geocentric universe. We are the center of the universe. It revolves around us because we're the basis. Also, to them at this time, Aristotle, who lived 300 BC, 280 BC, they believe if there's an object that's heavier than another object, it will fall faster than the lighter object. Makes sense. If something's heavier, the heavier one falls faster than the lighter one. So, I take this book and this piece of paper. The book is obviously lighter than a piece of paper. The book is basically over 800 pieces of paper versus one piece of paper. The book should hit the ground faster than the paper. So it makes sense. Galileo says, no, that's not right. So he goes up to the Tower of Pisa. It wasn't leaning at the time. It was the Tower of Pisa. Takes two cannonballs in different ways. Drops them in the Tower of Pisa. They hit the ground at the same time. That moment in time proves what the church teaches. The infallible church. Problem. He writes it up. When you go to school at that time, you're taught in Latin. So only special people are going to school first. Ones that are deemed that they can make sense of what they're doing. So Calvin goes up to the Calvin. So can be shared by all. That's what the church said. You need to recant what you just read. And also will be tested. His faith in the church is so strong, he's recanted it by saying, this is my belief. This is my theory. They still excommunicated him and put him basically under house arrest. Now, 1960, the church actually said, you know that Galileo thing? And they weren't. But why? If Galileo was, oh my gosh, this is actually right. Oh. Why don't you sit the ground and say, what? Perfect. Right. Okay. This has resisted air resistance. This has air resistance. Am I changing the weight of the paper because I'm blotting it up? It's still the same piece of paper. It's still weighing the same amount. What hasn't changed? Take away the air resistance, yeah, they hit the same time. But going back to the moon, David Schmidt, astronaut on the last moon, local students were on the moon. He took a hammer and a feather and a surface. No atmosphere. To prove Galileo right, he dropped the hammer and the feather at the same time. That's kind of, you guys got to realize, when they talk about that video how things are changing, knowledge is changing, what we can work with is changing, computer science, quantum mechanics, quantum computing. Why, what has happened from when I was a student and needing an entire room of computers down below on the next bottom floor to handle a message for me to send to another person, but now that thing is more powerful than that computer. This phone is more powerful than the computer power than they had in the Apollo mission. What's changed? The ability to store the information. We don't even have to store the information on the device. We want it to store somewhere else. Where is the cloud? Is it actually in the cloud? Who is accessing my information in that cloud? Security. You want to know how we protect security? That's right. Prime numbers is how to build security systems. Oh. Tangent aversion. So, position, and it's a parabola, always a parabola. Now, that's the wrong shape of the parabola because gravity would be negative. You would have y equals a negative x squared, and what that does to the parabola, transformation. It makes the parabola upside down. And that's the shape of everything that flies through the air. X cubed. Now when you have f of x equals an x squared, if you do f of 2, 2 squared is a positive 4. If you do f of negative 2, negative 2 squared is also a positive 4. Because it's a square, it's impossible to square something and get a negative number. It's always positive. Unless you put a negative in front. If I have a negative in front, then the negative would be in front of that number being squared. So there would be a negative in front after I square it. Then you could get negative, but it's not because it's a square, it's because that coefficient is negative. That's what we flip it upside down. But the square itself is always going to be a positive. When you do a cubic, when you do a power of 3, here's our power of 2. One, two, three, negative 1, negative 2, negative 3. Not the scale. So negative 3 goes in. We get positive 9. Negative 2 goes in. We get positive 4. Negative 1 goes in. We get positive 1. 0 goes in. We get 0. 1 goes in. We get 1. This is get the square. 2 goes in. We get 4. 3 goes in. We get 9. F of x equals x squared. Like this. I try to put in f of x as g. G of x is x to the third. I talked about these b, but this is not very deep. Negative 3 would be parentheses negative 3 to the third power. So g of negative 3, if I raise a negative to an odd exponent, the answer will be a negative, and 3 to the third is 3. That's off the scale. But it's down here somewhere comma 27. You plug in -2, -2, and then square it. The g of -2, -2. -2 times -2 times x is -8. -2 goes in, we get -8. -1. -1 to the third. -1 times -1 times -1 is -1. 0. 0 to the third. 0. So when 0 goes in, it's at the same place where that square is. We share the same point with 0. Or and then when you get to that other side of 0, g of 1, 1 to the third is 1. So then you share that point. G of 2 to the third. You've got 2. So 2 goes in, you get 8. So it's higher than the last answer. 2 goes in with 8. Positive 3 is 3 to the third. 3 times 3 times 3 is 27. So that's off the chart. Is there somewhere? We will get 27. So look at the shape. When you plug in negatives, because it's a 2, a negative to the third would be a negative number. These won't look better. No. And when you plug in positives, you get positive numbers. I have a touch of OCD, so I kind of make sure. But obsessed with it, I'll make sure this thing look better. X squared. Everything has to be positive. And then x cubed, because on the negative numbers when we do, they're going to be negative numbers. X to the fourth. Once you raise something to an even power, negatives are positives again. X to the fifth. A fifth power, if you raise a negative to an odd, it's going to be negatives on the other side. X to the fifth is this way. So odd exponents look like this. Even exponents look like this. Now, the only difference with even exponents and odd exponents, the closer you can get to 0, it gets a little flatter. Because when you raise your fractions to powers, they get smaller as the power gets bigger, the fraction is smaller. 1/2 squared is 1/4. So 1/2 to the third is lower, it's 1/8. And 1/2 to the fourth is lower, 1/16. So it is really wide, but then it starts to go up. Yeah, if you put a negative out in front, but that's not being squared, because that's not in parentheses. If I put the negative in the parentheses, that's something entirely different, and it will happen. So we're going to go. That's our cube. Now we have domain. What is domain? 2 words. Domain. Right. Alphabet. P, and then the R. So in terms of ordered pairs, domain would be your X's and array would be your. Domain is what you're allowed to plug into a function. What set of values can you plug into a given function? What's the goal? And the range is the y value, what's going to come out? Domain is what was in, range is what comes out. Domain is the x's, range is the y's. What you look for, again, we're going to cover more in depth when we get to actually look at the question. There is nothing that is going to exhibit an extra verse. There's no way to look at it without this. Is there anything that would make that undefined? No, because it's just an x squared. All real numbers, you can plug in anything from negative infinity all the way to positive infinity squared, you get an x. X to the third, you can cube every real number from negative infinity to positive. What number can you not provide? You can't have 0 in the denominator. You can plug in any number into the denominator as long as you don't have 0 there. So we have a problem when we get to 0. There's no answer for 1 over 0. So that means there's going to be a little break between the left-hand side and the right-hand side of 0. This is a rational. The key word is ratio. Ratio is fractions. Right here, x cannot equal 0, but it could be anything and everything else. So when you graph this guy, because you cannot plug in 0, there's something like it looks like a wall that moves up at 0, and it's called, I'm not going to put the name up yet, but it's called a vertical, because it's straight up and down. A vertical asymptote. Vertical asymptote. And it's a wall kind of goes like this. A little dashed line. And the dash line means you better not plug in that 0. Now, what I'm going to do is I'm going to plug in some numbers on the right-hand side first. Just some quick numbers. Here's 1, here's 2, here's 3. And then I'm going to take a really big number way over here towards the end of 10. Again, a huge number. You don't have to go through it. When I plug in 1 over 1, that would just get 1. When I plug in 2, 1 over 2 is a half. So it's halfway up between 0 and 1. When I plug x equals 3, 1 over 3 is a third of the way. When I plug in 10, it's 1/10. So what's happening is we are getting incredibly close to the x-axis. And as you continue to plug in x values to the right, they're going to be positive numbers. And no matter what I plug in, it's always going to be bigger than the 0. If I plug in 1,000, it's 1,000. It's still bigger than 0. If I plug in 1,000,000, it's 1,000,000. It's bigger than 0. It'll never equal the negative because I'm plugging in positive numbers. So from here that way, it's kind of lining up, being infinitely close to 0 without the x-axis. Never touching it. Now, you can't move 0, but you can get close to 0. If I plug in 1 half, I go halfway. F of x, 1 over f of 1 half. So that would be 1 divided by a half. How many times can 50 cents go into a dollar? Twice. 1 divided by a half is 2. Remember, and this is what, I have to do this with calculus because they get freaked out. Fractions are division. This is 1 divided by 1 half. What are you supposed to do when you divide? You're supposed to multiply by the reciprocal. So this is 1 time the reciprocal. So when half comes in, the graph is up here too. Exactly. If I plug in 1/4, I'm going to get 4. If I plug in 1/10, I'm going to get 10. If I plug in 100, I get 100. The closer I get to 0, this thing starts to approach positive infinity. But remember, I can never actually touch the 0 because as soon as I touch 0, I'm under 1 over 0 under 5. But it can be infinitely close, and the graph looks like this. Over here on the negative numbers, if you think about it, 1 over -1 would just be -1. 1 over -2 would be -1 half. 1 over -3 would be a -1/3. 1 over -10 would be a -1/10. 1 over -100 would be a -100. So it's approaching the x-axis, but from below. Because you're plugging in negative x's, so it's actually a negative y-axis. When you plug in a -1/2, you get -2. When you plug in a -1/4, you get -4. That's what this kind of graph, that kind of carrot function always ends up looking like that. The remaining is all real numbers. Now, this is how we would write it if we weren't math students. All real numbers except this. You plug anything you want to. But we're math students. So like here, the domain is all real numbers. So from negative infinity to infinity. Now here's the deal. You can't equal infinity. Infinity is not an actual number. It's a destination that you have to reach. As soon as you think you're at infinity, you're positive. By the way, what's infinity plus infinity? Infinity. There's different sizes of infinity. Think about, there's an infinite number of numbers greater than 0, right? And there's an infinite number of numbers less than 0. But isn't the size of all the numbers of negative? That's infinity as well. Isn't this infinity bigger than just greater than 0? Think about the number between 0 and 1. Just do half, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/148, 1/56, 1/512, 1/1004, 4,048, 4,436, 8,380. So that I can slice that up forever and never ever touch zero. Zero pair. Want to say 240. He was thinking about infinity way before. So what that means is there's an infinite number of numbers between 0 and 1. Just a fraction. Not to mention radicals. What happens if I cut it by the thirds? Of this? There's an infinite number of numbers between 0 and 1. Isn't that infinite smaller than all these? So there's different sizes of infinity. I got radicals. I was watching and lost that. Goes into the quantum realm because he continually shrinks half the size of an atom. You could technically even slice it forever. You couldn't. There's nothing smaller than an atom. Oh, wait, inside the atom, neutrons. What do you need? You got protons, electrons, neutrons. We can't press, we got quarks. We can't. No has on the light. Then you got quantum mechanics, you got quantum computing. What about ones and zeros? Yeah. And that's the concept that this evolves into when you get to the calculus. Because the calculus is able to infinity. The difference between the math that we do right now until we do the calculus. This is a stagnant system. You're doing math on a picture that's a statue. The moment in time it's frozen. In calculus, we do math while things are in motion. What's going on in that state? At this level, we can only find the slope in two separate points. Because when you do at the bottom of the slope, you subtract the x coordinates. We have to have two different x coordinates. In calculus, what we want to know, this is why it's easy. What's the slope at exactly 1 point or 1 moment in time? Well, at 1 moment in time, it's the same x coordinate, and if you put that in the denominator, 5 minus 5, you're dividing by 0. You can't do that. Newton thinks of a way to do it. You don't do 5 minus 5, what you do is you get something so we can approach 5 minus 5. It's infinitely close. Infinitely close to 5 minus 5. And depth in this case is the same as that. You know how to find in geometry, you can find the area of any polynomial, slice it in a triangle, or do whatever. Slice it in a square, a rectangle. We can find the area if it's a polygon. But what about curves? We can circles. But what about curves? Other things, parabolas. You know, the area that curves is doing happen. Slice that underneath there into an infinite number of tiny rectangles. And out of the area of all of those tiny infinite number of them as a number. And the exact area under that orbit. And we will touch on those concepts of how you set it up algebraically. But just one of the hardest things to do for a calculus is to do the algebra to get it set up. It's understand algebra first, and then you do the calculus. Square root. Asking about square root math. The radical square root looks exactly like the radical sign. First of all, domain. When we graph, we're only graphing in terms of real numbers. So no imaginary, no complex numbers, real numbers only. So the domain of a graph of the square root is limited because you can't plug in -1 because you can't get a real number. Like the square root of -1 or any negative number. The domain x would have to be bigger than 0. It has to be to the right of 0. Can you take the square root of 0? What times itself is 0? Zero is actually about 6. The domain is all x's have to be greater than or equal to 0. Okay, so let's see where you're at. That's how you write the domain using inequalities. Less than, greater than, less than, or equal to. That's not good. Because when you look back at the focus on it. When you write domains and ranges, another way to write it is using something called interval notation. When you convert inequalities into interval notation. So if I was going to do a number line graph, x is greater than or equal to 0, on a number line, right here at 0, that would be, because 0 has an equal, you would have a solid circle on the 0, and then you would shade everything on the number line to the left. And that's what the picture of it will look like. All real numbers greater than 0. Interval notation. Interval notation uses parentheses and brackets. Parentheses and brackets. So what we want to do is we want to convert inequality into interval notation. So this would be the interval from 0, comma, that arrow is going to positive infinity. Because you have equal to 0, it's a bracket on the 0. And because you're going to infinity, infinities are always parentheses because you cannot equal that infinity. If you can't equal it, it's a parenthesis. That's a little math 103, algebra 2. And it just depends whether or not people have seen this before or not. So if you have something like 3 is less than x, which is less than 8. So that means on a number line, here's my 0. I would have a, because there's no equals. Here's the 3, here's the 2. There's no equals. I have an open circle on the 3. I have an open circle on 8. X is everything in between. So it's all over. The interval notation would look like this. The value of x is everything from 3 with a parenthesis all the way to 8 with a parenthesis. Parentheses means it's everything in between except the endpoints. The endpoints don't work. If I do -5 is less than or equal to less than x, which is less than or equal to 4. So, -5, no equals on the -5, so that's an open circle. +4, there's an equal, so that's a closed circle. And x is everything in between those two numbers. That's what x is. So the interval notation, so we're going from left to right, -5 all the way to 4. There's no equals on the 5, -5, so that's a parenthesis. But there is an equals on the 4, so that would be the bracket. Kind of and I tried to get my algebra method of students to remember. When you have equals, you've got that little line straight right above. That means like a bracket is made straight up. Never put it on the minutes. So I'll come back to one of the rest of that. So the domain here. Now, square root of 0 is 0. You plug in 1. Square root of 1 is 1. Now, here's what you don't want to do. You want to plot nice points. You want to plug in nice numbers. The square root of 2 is approximately 1.414. That's not easy to plot. The square root of 3 is approximately 1.732. You don't want to do that as one of the things you want to do. What you want to pick are nice numbers that come out of square roots. So you want to pick x values that are appropriate to square root. So we get square root of 9. Square root of 0 is square root of 1. The next perfect square is 4. The square root of 4 is a 2. What's the next perfect square? Square root of 5, well, 6, 7. Square root of 9 is 3. So it's not going up very quickly. And the graph of the square root looks like that. Look at the shape of the radical sign. The graph of the square root looks like that. Looks like the shape of the radical sign without the little check mark on the left-hand side. Now we're going to shift it left or right, shift it up and down. We might squeeze it, squish it, flip it around. That's what it's up. That's the parent. Going back to this one, f of x is 1 over x. X is less than 0, or x could be greater than 0. But x cannot equal 0. So the left is 0, the right is 0, it's 0. This is what it looks like. if you were going to do the number line, right here at 0, there's no equal. So it would be an open circle, less than 0, everything to the left would be changed. Greater than 0, everything to the right would be changed. Interval location. That arrow is pointing to the left all the way forever. It's pointing at negative infinity. And if you notice the way I write my infinity, I cannot do a consistent symbol. When I write my infinity, I'm just going to stop with me. I gave up a long time ago. And then it goes and stops at 0. Now, what I told you was, you never put brackets on infinity because you can't get it. Right? And because that's an open circle, it's a parenthesis on 0. On this side, it picks up and starts parentheses at 0. And then the arrow goes forever to the right, so it goes to infinity. And that's the first. Now, we have to finish. Okay. These two graphs are joined together by the word or as an equality. We don't use the word or when we do mathematics. I mean, that's simple. This is the symbol. It looks like a parabola, but it's like a U or U. It's the union of those two sets, join those two sets together. That means union is or. If it's upside down, this symbol is intersection. Union is for the set of, now what is the answer? This set or in this set, this or this. Intersection is and. What's in this set and in this set at the same time? Where do the set overlap each other? That's what you're interested in. So these are the math symbols that represent union and represent intersection. So what you would do is you would join these two interval locations together with the U in between. So when you go and you're looking at the answers in the back of the book, you have to see it. I know yeah, absolutely. Jose? Okay. William? And Jose say. All right. Okay, I know, see you got, well, no class Monday. We work our tails off white nerdy and be here on Wednesday. Okay. And again, I will post this up on YouTube. I'll send you an email. And I will also send you the PDF of the assignment sheet. All I need you to do is try to get started on 1.1. That's about it.